CBE 320, Lab Experiment 2, Heat Exchanger, Shell and Tube specifically. We have an introduction, goals of the experiment, preparing, literature, resources, experimental setup, the interim report, the final report, and extra credit. There's also appendices A, B, and C. So this table of contents is very similar to the first lab. Starting with the introduction. Heat exchangers are ambiguous in the chemical industry, as chemical engineering operations are conducted over a wide range of temperatures. Some common applications are heating and cooling of reactors, vaporizing and condensing streams and distillation columns, concentration by evaporation and cooling crystallization. Suffice to say, most unit operations will include numerous heat exchangers to modulate temperature. Heat exchangers come in a wide variety of shapes and sizes, such as flow rate, temperature, phase of the fluid, corrosivity, fouling characteristics of the streams, and physical location affect the selection. Given their wide use, it is important to have a sound understanding of the basis of their selections, designs, and operations. One common type, namely shell and tube heat exchangers, are constructed by enclosing a number of tubes in a cylindrical shell. This generates a large tube surface area, shown in Figure 1. Heat exchange occurs between the hot and cold fluids that flow through either the tubes or the shell to segregate the fluids. Countercurrent flow is the preferred mode of operation, as it maximizes temperature driving force, that is, needed for heat transfer. Countercurrent flow is the preferred mode of operation, as it is maximum for temperature driving force for heat transfer. So in this experiment, you will be working with a single pass shell and tube heat exchanger with countercurrent flow. As an engineer, you will be designing heat exchangers to exchange heat between the hot and cold streams in the most efficient manner. I have the words in quotes as the definition of efficiency itself can vary as indicated in the question 2 in the following section. A straightforward way to describe, model, the rate of heat transfer per unit area, kilowatt per squared meter between two streams, is to depict the transfer rate as the ratio between the driving force and resistance to the transfer. In the current case, the driving force is the temperature difference. The shell and tube slide films, metal and fouling layers impede or resist the heat transfer. The transfer rate can be expressed as the ratio of driving force and the sum of resistances. The difference in the temperature of hot and cold fluids, delta T, will vary along the length of the exchanger as their temperatures continuously decrease or increase. Subject to a few constraints, it can be shown that the temperature deriving force can be estimated as equal to the LMTD, log mean temperature difference. In place of resistance, a commonly used expression in heat transfer applications is to use the term heat transfer coefficient, which is the inverse of the resistance. We have U, A times delta T, LM. This is equal to Q. This is equal to the heat transfer. The heat transfer rate, A is area, U is heat transfer coefficient, LMTD is long mean temperature difference, degree Kelvin. In this experiment, a simple model for heat transfer rate and coefficient using straightforward heuristics to describe the system should be developed using the DOE methodology. The results will be compared against literature correlations subsequently. The simple model is based on the following heuristics. The tube side resistance will be significantly impacted by the flow regime, laminar, transient, or turbulent. Refer to the PowerPoint presentation on HX experiment. For the reason behind this assumption, the Reynolds number RE ranges from laminar, transient, and turbulent, respectively. They are 2100, 2000 to around 4000, and 4000. The shell side fluid resistance is significant. As the transition to turbulent flow regime would occur at low RE due to the mixing effect of baffles, the flow is expected to be turbulent at all the test flow rates. Hence, the coefficient is modeled as varying linearly with flow rate. The effect of temperature driving force will be tested by varying hot water temperature. The effect of temperature difference on heat transfer rate is linear, and assumed the effect of orientation on heat transfer is not known for paleological regions. The overall heat transfer is expected to vary along the qualitative lines shown in Figure 2. The effect of increasing tube side flow on overall U is more significant. When the shell side flow rate is high, as evidenced by the steep slope of the line, this points to interaction effects between the flow rates that could be included. The effects of all other factors are expected to be negligible at the experimental conditions. Goals of the experiment. 1. Develop an empirical correlation for heat transfer rate and heat transfer coefficient using the DOE design of experiments methodology for a range of conditions listed in Table 1. A constraint is each trial takes 15 minutes to execute. The observation for the experiments should be made at steady-state conditions, and refer to the PowerPoint presentation to review, and also review the introduction to DOE. Table 1. Factors considered in the DOE model. Variables and conditions. The variable is the tube side flow, the tube side inlet temperature, the shell side flow, and the orientation. Okay, so the conditions are laminar, transient, turbulent, pump capacity would limit the maximum tube side Reynolds number to about 6,000. Tube side inlet temperature, two extreme points 40 and 65 degrees Celsius if the experiment is performed in the spring semester, and then choose temperature range of 27 to 52 to account for the colder, warmer. Two extreme points 40 and 65 degrees Celsius. If the experiment is in the months of January through March, you can choose your temperature range of 27 to 52 degrees Celsius. Moving on, approximately 1 and 5 liters per minute, and horizontal and slanting up. Even when closed, the steady state, some fluctuations in temperature readings will occur due to inherent system noise. Steady state conditions, in theory, should take an infinite time. Practically, a steady state is reached in the experiment in a few minutes. Assume steady state when temperature begins to fluctuate up and down. Take the average of the last 3 readings by noting the values manually. 2. Using the observed trends, determine A. Conditions that maximize the heat transfer coefficient. B. Conditions that maximize the rate of heat transfer rate. C. Conditions that minimize the approach temperature. The cold and hot streams in any heat exchanger have an associated heat capacity value equal to the stream's flow rate F and specific heat Cp. Since the flow rates and heat capacity of each stream are typically different, the heat capacity of steams will not be equal. The approach temperature should be calculated as the difference in the steam temperatures at the exit for the steam with the lower heat capacity. 3. At a theoretical level, multiple factors affect heat transfer in a system. Identify the parameters that impact the overall heat transfer coefficient U for the heat exchanger, and refer to the PowerPoint presentation. Compare the heat transfer coefficient values of your trials against those estimated from correlations in the literature. So, compare your theoretical and measured values. Preparing for the experiment, the overall heat transfer coefficient. Preparing for the experiment, The overall heat transfer coefficient at each condition is a function of the shell and tube side resistances, fouling, and the metal resistance as described in the textbook by Gene Coppolis. Review the material in the textbook and the video I have posted regarding the experiment. The video provides a brief overview of heat transfer theory and describes the application of DOE methodology in planning and analyzing the experiment. The following activities should be performed prior to the day of your laboratory experiment. Students should rotate through the different experiments. You should watch and learn through the setup, and you should also take the quiz. And then each group should submit their plans for the experiment. Appendix B, advanced planning, describes the contents of your planning reports. Since you are submitting the experimental plan electronically, it's not necessary to repeat that information in the lab notebook. Just state the headings of your topics in the planning submission and 1 or 2 line description, then refer to your electronic submission for a reminder of the details. Comprehensive instructions for designing an experiment and analyzing results using a DOE program in JMP have been provided in Appendix A. Analyze your results both by plotting your results on a piece of paper, then supplement your analysis with JMP. I'm recommending this as your eyes are a great pair of statisticians. And there was also a note. They said the optimum conditions for 2, 3, and 4 are not the same. Here is the literature resources. We have arm field, shell, and tube heat exchanger. We also have the textbook, and then we have the presentation notes. Experimental setup. Refer to the manual for operating the heat exchanger and collecting the related data using the LabVIEW software. The level of water in the tank should be sufficiently high to immerse the heating coil. Drain the water in the tank at the end of the day. And then the interim report. Answer the following questions in the interim report. The response should consist of only the relevant sample calculations. No written description is required. When possible, provide the answer in the form of a graph or a table and list the relevant equations. Besides presenting the results, you should also briefly review your results for statistical significance and outliers and alignment with theoretical predictions. So we have, it seems, 7 points until we hit the final report. Point 1 is provide an example calculation for Reynolds number that supports your tube side choice for flow, regime, laminar, transient, or turbulent. And what do the results of the DOE analysis predict for the effect of shell and tube side flow rates, hot water inlet temperature, and heat exchanger orientation on an overall heat transfer coefficient? Are the predictions reasonable based on your physical understanding of the process? And then calculate the log mean temperature difference at each trial condition. Show one sample calculation. So here's what we want. Log mean temperature difference, Reynolds number. And then 4, calculate the heat transfer coefficient at your trial conditions based on your observations. The number calculated by the software may be slightly different as the software is using the flow and temperature values not at the same instant as you. For your report, use the values calculated by you and remember to show one sample calculation for the heat transfer coefficient. Oh, okay, so we're saying u is the inverse of just 1 over r, because we have q equals 1 over r times a times delta t. So u is just 1 over r. So if you want to calculate the resistance, if you want to calculate, the heat transfer coefficient, you'd have to solve this equation for u, put q over to the left, put a over to the left, put delta t over to the left. We'll have the area for our pipe, we will have the change in temperature for the pipe, and then we will also have the heat transfer coefficient for the pipe. And then point 5 in the interim report, estimate overall heat transfer coefficient based on standard empirical correlations. Gene Coppolis, page 255. And then pick 3 trials wherein the hot water flow rate was greater than, equal to, and less than the cold water flow rate. Estimate the maximum heat that would be transferred assuming the heat exchanger is infinitely long at each chosen situation. And then a tip. In a heat exchanger, there is a hot and cold stream. The gap between the existing hot and cold streams will reduce as the exchanger area increases. For an infinitely long heat exchanger, the temperature force will be 0, or for an infinitely long heat exchanger, the temperature force will be 0 at one or both ends as indicated below. When the heat capacity of the cold stream is greater than that of the hot stream will be cooled to the incoming cold stream temperature. When the heat capacity of the cold stream is equal to that of the hot stream will be cooled to the incoming cold stream temperature, and the cold stream will be heated to the incoming hot stream temperature. 7. Estimate the efficiency of your heat exchanger as the ratio of actual rate of heat transfer from the hot stream to the maximum possible rate of heat transfer. Assuming the exchanger is infinitely long, you can see question 6 as well. That's a hint. For the final report, we're finally there. The final report should address your objectives of the experiment. In addition, discuss the trends for rates of heat transfer versus efficiency defined in question 7 of the interim report. As you vary the conditions of your experiment, it is important to mention items that went well, those that did not, and any interesting observations you made and recommendations for improvement. The report should follow the format for a long report. We have extra credit. 1. Estimate the overall heat transfer coefficient assuming that the tube and shell side flow rate are 50 liters per minute and the respective inlet stream temperatures are 65 degrees Celsius and 20. A. The empirical correlation developed using JMP, and then B. The literature correlations for heat transfer. Compare the two numbers, which value is more reliable and why. We have Appendix A. A procedure for designing experiment. DOE is a branch of statistics that deals with the planning and execution of controlled tests and interpreting the results of the test. Typically, the processes and experiments are conducted to identify and qualify the impact of parameters on a process. Several experimental designs were developed prior to the advent of computers to identify and quantify the impact of parameters on a process. These designs did not have a mechanism to account for any knowledge an experimenter may possess about a process, even if the knowledge is only partial, and constraints on resources. Stated differently, the designs did not have the flexibility to adapt the design to each unique situation. The shortcoming has been addressed by custom DOE, as it is possible to fine-tune designs to suit the specifics of a problem and ability of resources. I have illustrated a custom DOE case by stepping through the heat exchanger experiment example in JMP. Given the paucity of time, I will be touching only a few key features. Even so, I hope you can observe the power and procedure and would consider DOE as an option whenever you perform a controlled experiment in the future. The JMP manual contains more information. When conducting the experiment, it is critical to follow the conditions and sequences for the trials as prescribed by the program. Appendix B. Experiments should be thoroughly planned. Always start with the end goals in mind. First, learn about the operating procedure for the instruments. The goals for each experiment are stated in the respective objectives sections. For each goal, identify the factors that are varied, the independent variables, the factors that are held constant, the controlled variables and the output dependent variables, and the nuanced variables that are not well controlled but might affect your results. Then check if your procedure varies the independent variables efficiently. Procedures are in place to keep the control variables at target. The outputs can be measured accurately, and the impact of nuanced variables are minimized. For example, when a system model assumes a steady state, your task is to decide how you would decide or what steps or observations you would pursue to get your system close to steady state. Similarly, when making a measurement such as density of a solution, consider the steps that would give repeatable and correct results. Include enough of the math development and analysis to tie your observations to the goal. The math analysis helps clarify what you are doing and why, and can help you avoid errors in planning. Supply a few key literature citations. Does not have to be a comprehensive bibliography. All of this should be sufficiently clear and complete so that your boss or instructor will be confident you know what you're doing and how before you start the lab. One final note, don't overthink your plans, as some responses could be as simple as turning the dial on the instrument, relating the information in the instructions, or inputting a value on the controller. Appendix C. Differences between Armstrong manual and the lab instructions. The manual proposes measuring the temperature efficiency for the hot and cold streams. Appendix C, to monitor heat exchanger performance and calculating the mean of the two efficiencies. The differences in the heat capacity of the two streams is not considered in such a definition, which restricts the application of the results to systems that have cold and hot side fluids with equal heat capacities. Two commonly used versions of heat exchanger effectiveness that account for heat capacities of the streams. Two commonly used versions of heat exchanger effectiveness that account for the heat capacity of the streams are: 1. The ratio of the actual rate of heat exchanger transfer to the maximum possible amount of heat transfer that would be the case in an infinitely large heat exchanger. 2. The approach temperature, which is the absolute difference in the temperature of the exiting stream with the lower heat capacity and the incoming stream with the larger heat capacity. Normally, a 5 to 10 degrees Celsius temperature approach is considered economically. However, the number can vary widely depending on the situation. In this experiment, we define effectiveness as the ratio of actual to the maximum feasible heat transfer rate.